uh, um, stop my video so that you can be completely focused on Paco. So let me kind of give you some context for the rich context. Um, we were set up in response to the Commission on Evidence-Based Policymaking. So I expect you're not so familiar with this, but this is an initiative in the United States that has captured a lot of attention. It was trying to figure out at the federal government level how the government could better use data to inform policy. By way of context, the GDP, the government sector accounts for between 20 and 25%. And if you count state and local governments, about well over 30% of economic activity in the United States. And while in the private sector, using data and analytics to inform decision-making is commonplace, it is not so common in the government sector. So the commission, there was a commission that was set up by Paul Ryan, then Speaker of the House, and Patty Murray, who is the ranking senator from, or third ranking senator from the state of Washington. And what they wanted to do was to appoint a commission that would inform the government on how to make decisions better. So as Tiranka pointed out, I had spent a lot of time with the Census Bureau. The Census Bureau asked us to build a secure environment within which confidential data for decision-making in the United States, wait a minute, Paco, that's a bit too soon.
Oh, okay.
Can you go back? Can inform decision-making. It's data on human subjects and businesses. So we put together the Administrative Data Research Facility that showed how people could put the data together. However, simply getting the data in one place is necessary but not sufficient. You also have to train people in how to work with the data, because in order to make evidence, you have to be able to think about what the questions are and converge them. So we also produced an applied data analytics training program so that people from different agencies as well as researchers could combine the data together. Anyway, that was very successful. The report generated legislation, so that's the next slide. The Foundations for Evidence-Based Policymaking Act, which was passed in December of 2018 and signed into law January of last year. 10 of those recommendations were passed into that law. Combined with that is also the federal data strategy. So that's the next slide, which is requiring federal agencies to use data to make decisions. So you can see data needs to answer agency questions, build staff data skills. That's obviously what we've been doing. Assess data maturity, identify priority data assets, and publish and update data inventories. So you could do this by hand, right? How do you identify data assets? How do you figure out what's the best area to produce? And and you could by hand publish data inventories. The problem with that is, if you're going to use data science, you may as well use data science to address all of these issues. So kind of the third step and the inspiration for this is, how can you use data science to help the government use data for decision making? And that's what rich context is really about. We want to not just produce a list of this information, but also identify for the government what the most useful thing is. So next slide. So these are if you want to take a look at these, the Foundations Act, the Information Quality Act, the Federal Data Strategy, and the Year One Action Plan that just came up straight before Christmas this year. So those are the underlying federal activities that are going on. And I should say I'm half-time at the Office of Management and Budget working with them on this. Next slide. So the advantage of what we put together was we put together a secure environment. We actually won a National Government Innovation Award on that, which enables agencies to share data. Next slide. We built this secure environment in which data users can work with the data, confidential data, and collaborate. And then one piece of this interaction was also to build metadata code and tools so that when you land on data sets, you actually understand who else has worked with the data, for what purposes, what code they used, and so on. Turns out that's a big challenge because, as any of you who have worked with data know, it's very hard to get people to, it's very hard to find out what data have been used for what research, what code has been used, what tools have been used. So our big insight here was the information about who has worked with data, what tools were used, and so on, is embedded in social science or scientific publications. In any publication that uses data, the researcher or the analyst will say, this is the data set we used. This is the key concept. How do we find, out of 80 million publications, how do we find what data set has been used? What we need to be able to do is to read the publication, find from the semantic context the section in which they say, here is the data set, and build natural language processing tools and machine learning tools to find the data set and highlight it. Because once you've got the data set to publication link, you can figure out the publication, you can figure out the authors, you can figure out the topic, you can figure out the methods. So that's what we call rich context. Next slide. So to summarize, what we're doing here is creating a secure environment. We are building the skills to link and analyze the data. And then the rich context is showing what the value is of finding the data so that the people who are providing the data, the government agencies, can say, there were 100 publications published using this data set. Here are the results. Here are the findings. And they can do that automatically. So when they publish a data, so that helps them identify their most important data assets because they can find which data sets were published most often and in which fields that are most linked to the agency mission. And when they put up a data inventory, instead of just having a random list of data sets, they can choose to rank the data sets by the ones that are most important. So this is very different from the open data movement of 10 years ago, in which agencies just put out a random list of data sets that weren't particularly helpful. Now what you're able to do is inform both decision makers and the public how the data are used in decision making. They provide the evidence-based policy making. Next slide. Take it away, Paco.
All right. Thank you very much, Julia. So to get into more of the details then about how machine learning and natural language and knowledge graph are used here, uh, there's a need at the point at which an analyst or a academic researcher is working with these data sets. There's a need for better search and discovery regarding use of these data sets, and in particular, search and discovery regarding, again, as Julia said, who has worked with the data before, how have they used it? So not just understanding uh, what the data set entails and what kind of metadata is there, but a broader context, a rich context, if you will, of the people who are the experts, as well as the topics and the tooling. So our objective is to provide that search and discovery. And the method that we use is to collect, on the one hand, parsing PDFs of research publications. On the other hand, we're also collecting usage telemetry, log files, if you will, from the analysts who are working uh, doing analytics work with data sets uh, in the ADRF platform. And I'll show in a bit how we've
Paco, we
worked to
forgot.
extend Jupyter.
Paco, we forgot to tell them, of
Yes.
course, the setup for this is we want you to be involved. So we are very much hoping that as we're
Yeah.
telling you this, you are thinking about how you and your teams can contribute to this international effort. Go ahead, sorry.
Great. Yeah, that's an excellent segue. A lot of what I'm showing here is sort of we're building up a map of the community for a number of different inputs, components that go into this overall effort. Most all of this is based on open source, and it does intersect with several different communities. Uh, as I mentioned, there are parts that are natural language, that are parts that are knowledge graph, parts that have to do with recommendations, etc. Um, and so to show a little bit more here, here's a visualization of the latest corpus that's in a machine learning competition that we're running. And I'll talk a bit more about that competition, and that in particular is one of the ways to really get involved with this. The focus is on socioeconomic impact. Definitely, there's been a lot of support from different groups, funding through Schmidt Futures, Sloan Foundation, Overdeck, and others. There's partnering with Bundesbank, with USDA, and also collaboration with Sage Publishing, Repic, ResearchGate, Digital Science, and other providers for scholarly infrastructure. I should mention that this graph here is it's really a subset of our knowledge graph, but it is the portion of it that has open access PDFs. And so in the graph, the dataset providers, which are typically federal agencies, state agencies, municipal agencies, in some case commercial providers, they're listed in orange. And then the datasets themselves are listed in red. You can see some points in the graph here where there's a very central node that's in red. Uh, the research publications are in blue. The journals are in green, and then the authors are in purple. And we can talk more about some analysis of this graph. You can probably see that there are definitely clusters here. Large portions are adjacent to USDA and some of the data sets they work with. Up in the very top, much more adjacent to Deutsche Bundesbank and some of the economic research, mostly out of Europe. Uh, so again, the challenges that we're addressing is that for a given data set, can we find out who's worked with the data before, what methods and code were used, and what results were produced? So a big part of how the different parts are integrated are through use of knowledge graph. And by having a graph for our representation of metadata, that provides us with a lot of flexibility. Many of the sources that are coming in have different degrees of data quality, different degrees of errors that we see that need to be corrected or repaired in some way. So by virtue of having a graph, we have a lot more flexibility to incorporate a wide range of very noisy data. And also by virtue of having the graph and graph analytics, we can measure the quality of the metadata. There are very good algorithmic means for that. And moreover, this allows us to prepare features to be used downstream in machine learning models. The models are initially for creating links that are not explicitly expressed in research publications. So when you publish a paper, there's definitely metadata to describe who is the publisher, who are the authors, what are the topic keywords. But there's no explicit metadata to describe which were the data sets on which this relied. Now, that's a changing landscape. There's certainly a number of initiatives to capture research objects for published research. I know that Nature and some of the other leading publications have new requirements along these lines, but yet there's a backlog of so many millions of publications that are essentially just PDFs. And so we will need machine learning models to be able to go in and effectively mine that backlog of publications. Secondly, though, the machine learning models are used for recommenders. And again, connecting the analysts with who are the communities of experts, what topics are being researched, what kinds of tools are being used, et cetera. And then thirdly, also there's the mission to engage the public. The automated data inventories that are mentioned by the new laws, they also speak to not just engaging researchers, but how is this information being made more accessible for the general public? And then there are some other more long-term efforts we'll talk about in terms of helping to train analysts. As Julie mentioned, a large part of this concerns the training. And as new analysts come into these roles, they face a lot of learning curve trying to understand a number of different data sets which they need to work with. What are the different what's the different explanations for each column of each table and each data set? How can they struggle with that learning curve? Can we provide them tools to accelerate that learning? And then lastly, there's a very large goal in terms of identifying what is the impact of these data sets on public policy. Can we use graph methods to help quantify those impact metrics? So to look into the methods that we're using then, number one, quite frankly, there is a lot of manual work, as I've found in any AI project. There's a lot of work in terms of manual curation, making sure that your data ingest is working correctly, being able to spot check and validate unit tests and consistency checks and the rest. So we have a team. We've been developing rules, essentially our own adaptation of Agile methodology and use of Git within a small team context to be able to manage this curation. But also we look to how can we automate as much as possible? How can we augment what the people are doing through automated means and machine learning? Whenever possible, we are employing persistent identifiers. I'll show that in the graph, but definitely making use of DOIs, ISSNs, RARs, ORCIDs, etc. And there's definitely a lot of areas throughout our workflow different stages where different types of machine learning can be leveraged. Primarily, we're talking about inferring missing metadata, whether we're talking about entity linking or self-supervision being used for that. And I can go into those individual use cases. One of the things that we found while we were beginning to work on this was that while there are a number of different discovery services available and APIs, one of the problems that we faced was being able to compare results across multiple APIs. And so we have an open source project regarding that, how to federate queries. We use this for being able to understand metadata errors, effectively how to triangulate on metadata errors by comparing different views of the same complex objects and their metadata. And then the other part of this is that in addition to all the automation, we're using human in the loop, several different ways of incorporating feedback loops, initially through semi-supervised learning, but then other forms of feedback as well. And the idea there is that when we infer missing metadata by use of a machine learning model, we can also get some estimates, some measures of uncertainty from those machine learning models, uncertainty about the results. And we can use that as a threshold test to determine for the results which are less certain, we can throw those out to the community of experts, effectively going out through the discovery services such as Repic and others, where we can get feedback directly from the authors. So this is interesting that we have a group of people trained to be doing the knowledge engineering, if you will, the metadata curation. We have the machine learning to help correct and infer missing parts. But then we also have people coming back in and developing feedback for those results. So it's a fairly complex workflow, but it does try to make the best of both worlds of where people can provide expertise and where automation can augment that. And then the last point here, very importantly, so much of the most vital information that we need is to be found within the libraries and is curated by professional librarians who understand the nuances of the metadata, who have much of the history about the data sets, and they understand the linking in practice. And so a lot of what we've learned and are continuing to learn now are really what are the best ways that we can collaborate with these librarians. So let me shift a little bit into our research methodology. In terms of our process for developing knowledge graph, up in the top right, the goals that we're reaching for are to represent and understand and recommend who are the experts, what topics are emerging, because sometimes that is a surprise, and what kind of methods and tooling have been used and can be understood. And to put this in context, when we're working with the agencies which produce these data sets, oftentimes they have very little visibility as to who their expert communities of users are. Case in point, there was recent research that emerged about changes in migratory bird patterns due to climate effects. And the research depended on some of the ocean data observation, which is being produced from NOAA, NOAA, and NASA, and others. And the agencies had no idea that this research was dependent on their data or that it was emerging in this way until after a lot of it had been published. When they do understand who the experts are, they can engage with them and they can work with find if there's better ways that they can produce these data sets or other features they might need. So that's a lot of what this diagram shows, is that the agencies are starting out really at the level of activities. They have curated data sets. These data sets get used by research projects. And then the outputs from those research projects are published research. So in the middle, in bold, the things that we can actually see are the activities, the outputs, the outcomes, and then hopefully what impact those have. And we know that there are curated data sets. We know that there are research projects. We don't necessarily have a directory of all the projects that are active, but what we do see as tangible outputs are their published research. And so the question becomes then, how can we track the links between these, especially for the parts we don't have direct visibility? Can we use machine learning models to infer these links and track this linkage and effectively measure this behavior? So in terms of constructing a graph to represent these activities and outcomes, we will take as ground truth, we know of the data sets and we know of the providers for these data sets. We can either manually curate or infer by machine learning models the linkage between the data sets to the publications. And then once we have the publications, of course, then we can start to track the links from them to other entities. So for instance, here I've shown once we have publications, then we know what journals they have. In addition, we know what authors, and then for the authors, we can track their affiliations. And that metadata, that linkage is all available through the discovery services, their APIs. As well, there are topics, keywords, subject headings, that is to say all the same. And to some extent, we can track from the publications what methods are being used, or at least we can infer that part. And then I should state that policy has effect throughout this graph. However, one aspect of linkage is what is the effect of this published research on public policy? So, effectively the challenge there is, can we draw linkage between publications and policy? Now, as I mentioned, persistent identifiers play a very key role. They allow us to weave together results from different discovery services. So, of course, for publications, DOIs are being used as URL redirects for many publications. For journals, there are ISSNs. For authors, there are different types of persistent identifiers, but ORCID is one of the preferred ones. There's, of course, also BIAF and other types of identifiers. In terms of topics, typically we'll see topics being represented in something like PubMed's MESH, or perhaps Library of Congress subject headings. If it's geospatial data, there's the NASA, I've got it on the next slide here, but there are different identifiers for these, URIs for them. When it comes to organizations, one of the emerging persistent identifiers is called a ROR. So the agencies that provide data sets, as well as the commercial providers, typically all have RORs assigned. And we see this increasingly for the research projects that agencies, universities, et cetera, in terms of author affiliations, we can also assign RORs for those. At the bottom, there's a link if you want to go into more formal descriptions. We have the ontology definitions described, and we have a controlled vocabulary that blends from other controlled vocabularies such as DCAT and CITO. So now, as far as usage, this knowledge graph representation spans across really three different areas of practice, three different domains. On the one hand, when we're talking about providers and data sets, this is generally represented in terms of data catalog. And so you see ontologies such as DCAT, which are popular for representing that. When we're talking about topics, this is typically subject headings. This is the kind of thing that you would get out of Madsref or Wikidata, DBpedia, etc. And I did mention down at the bottom there, PubMesh, also geospatial data uses the GCMD, and Eurovoke is a similar kind of subject heading in Europe. But then on the left-hand side, when we start talking about the authors and their affiliations and the relationships between publications and journals, that's typically represented in scholarly infrastructure. And so we have the discovery services, which are sharing metadata. And there's a number of these that we've worked on for integration. On Paywall is really excellent, showing where the open access PDFs are. Digital Science has the Dimensions API. Repic is very popular amongst economists. Of course, ResearchGate, Crossref, and Datasite are very popular. Increasingly, I'm finding so much value out of the European efforts for OpenAIR and its related Scholar Explorer. There's also PubMed in Europe, PubMed, Semantic Scholar, Elsevier, SSRN, etc. The point I really want to stress, though, what's interesting about this work in Knowledge Graph is that these three domains, data catalog, subject heading, and scholarly infrastructure, they don't have a lot of formal linkage. And in particular, we have not found any previous work that had formal linkage between data catalog and the scholarly infrastructure. I know that Datasite and some others have been working toward that. Dryad is another one. But there wasn't any real ontology standard that we could reuse. So that became part of the control vocabulary that we had to develop to be able to merge those two together. Now, once we have this linked data, this metadata that we can build into a graph, then people, different feedback loops based on experts get involved. We have our team at NYU, a number of grad students who are trained to work on developing Knowledge Graph. And, they're doing a lot of manual curation in addition to the automation. But then, as I mentioned, we also go out to the expert communities, to the authors, and get their feedback for other human in the loop. And again, that really addresses a lot of the data quality or metadata quality issues in the graph. Ultimately, though, one of the major outcomes is to be able to quantify the impact of data sets on policy and using the graph representation and graph analytics for that. And so to do this work, we have been developing a number of open source projects. These are all available on GitHub under our organization Coleridge Initiative on GitHub. There is one coordinating repo called RC Graph. This is where we handle our knowledge graph management, effectively the workflow for being able to develop knowledge graph. And it has a number of different submodules. If you're familiar with using Git, basically we have some links into other repos as submodules. There is an open source project called richcontext.schol API, and this is something on which we also invite participation. It's available on PyPy, and you can bring it in through pip or install it through Anaconda. But it federates the different discovery services, and currently we have about a dozen, and we are adding more to be able to do federated queries across different APIs. Part of the problem is that the different APIs, some produce JSON, some produce XML, they have a variety of different formats. We wanted to be able to federate queries and come back with some consistent formats. In addition, we wanted to be able to measure quality of the metadata coming back from these services. And so understanding recall, how well, what kind of success rate do we have when we're making queries there? What do the performance analytics look like as far as the response? What the error rates are that we measure within them. And we have a paper in the works where we are describing across these different data discovery, metadata discovery services, again, what some performance benchmarking, some error rates, etc. There's another project called ADRF Onto that is our controlled vocabulary that we're using for representing the knowledge graph formally. It's based on OWL. Really, it's based on SCAs to understand the relationships in search and discovery. But it incorporates DCAT for the data catalog parts, PAV for provenance, Cyto and Fabio to have the scholarly infrastructure citation graph, and others. And the endpoints for the schema for that integrated vocabulary, that's available on the wiki of that repo, that GitHub repo. And then lastly, the main one is, it's called RCLC. It's a machine learning competition, and that is structured based on leaderboards, like we see with NLP Progress and Papers of Code. And I'll go into that into more detail. But there's an article that we wrote recently to describe the different areas of machine learning which are being used in rich context, and the areas in which we are working with different communities, different open source communities, working together toward contributions on this project. In addition, we have been working with Project Jupyter and helped to arrange some of the funding for Project Jupyter. I have a lot of background working with Jupyter. I was co-chair for JupyterCon and have worked very closely with Fernando Perez and Brian Granger and other folks in that community. Julia worked with Fernando and Brian to secure funding for a project which extends Jupyter Lab. There are really three main components on these extensions. One is the ability to register data sets. So when you're working with known data sets, can you provide URLs, essentially a YAML fragment that points out to a canonical definition for those data sets, and then along with it, pointing to where is its metadata available. Secondly, there's a metadata explorer in Jupyter Lab. It's an extension, and it allows an analyst to be able to browse the metadata, to be able to walk the metadata graph, if you will, instead of clicking through URLs as you would with a web document, you're clicking through on the IRI definitions for the metadata. So if you have a data set that you're beginning to use and you register it in the Data Explorer, then you can begin to see essentially a data frame view of it, all the different columns. Every column will link out to its associated metadata, and you can click through to find the trail of where did this column come from, what are the standards attached. For instance, if it's a date value, what are the definitions of the values within the column, or if it's foreign keys, were there any previous problems that other analysts had? And then thirdly, there's a matter of feedback loops. On the one hand, when analysts are working with data sets and doing data science work, there is the ability to add commenting. So essentially adding annotations. If you're working with a data set and you find that there are problems, you can annotate that with a comment to describe perhaps what might be needed to improve the data set or correct some sort of error. And then these comments can go back to the data stewards. They propagate back through. So there's a new set of features called telemetry that's going into Jupyter that's used for part of this. And this allows for privacy-preserving extensions so that within an organization, when people are working in Jupyter, we can collect log files to represent that usage, and any annotations that come out of the comments, those will propagate through the telemetry. Any usage of data sets propagates through the telemetry. This allows for reporting about usage all the way back to the data stewards, as well as any suggestions for correcting errors. So it's a very rich set, and the interesting thing is it's all being managed as extensions in JupyterLab, and really with just a few lines of JavaScript, any one of these components can in turn be customized for a given organization or use case. Saul Schonenberg is one of the programming leads, developer leads on this project Jupyter, and he's got, he tweeted out here, but he's built up my binder instance to be able to demonstrate how these rich context features in JupyterLab work. And okay, so let me progress into talking about the leaderboard competition. We had the original, or the initial rich context competition was in late 2018 through early 2019. So it concluded approximately a year ago. We had several teams from leading AI organizations which competed in that. Allen AI Institute took the top place in terms of model ranking for the commercial category. And then KAIST in South Korea took the first place for academic. And we noted from some of the results from the teams, we noted their suggestions of how they would improve competition. And so this past year, beginning in about July this past year, we took the competition and we moved it public. It's based on GitHub, and so there's this repo for it. We changed it so that it would be a leaderboard competition as opposed to more of a private Kaggle style. Instead, we're making it very similar to NLP Progress or Papers with Code, where every submission onto the leaderboard has an associated GitHub repo for their modeling, and the corpus is all open. The results are all open. People can replicate the research themselves to confirm the results. One of the things that we noticed was, of course, that if you need to have really high quality test sets within your corpus, and so one of the enhancements that we did while we were developing this leaderboard competition this past year was to focus on highly curated test sets to confirm within our golden standard that whatever's going in there has very high quality. Also, we shifted the competition so that it was only based on open access PDFs for publications. Again, so that this could all be open, it could all be reproducible by many different people. One of the things that we've noticed by shifting to having an open competition is that the teams who are competing, they actually end up collaborating together. We see a lot of collaboration, discussion through GitHub issues, email, etc., where they're identifying data quality issues in the corpus. They're helping to develop tools which are shared across teams, and it's been very heartwarming to see that collaboration. Ultimately, the goal.
Just to motivate you in this, one of the reasons we were thrilled that Titakar reached out to us is that we'd very much like to see you participate in this competition. We'd very much like to see your names up on this state-of-the-art leaderboard.
Very, very, very much so. We've had a couple of the teams, as is shown in the bottom there, KAIST and Lark, have come in and resubmitted for a recent re-release of the corpus here for this open leaderboard competition. And now it's available Every different release of the corpus has a get release tag. So you see down there, we have some results noted for release 015. I believe we're up to 018 though now. This corpus is something that we haven't really found comparable types of open corpus elsewhere regarding open access PDF for research publications linked to datasets. Part of the emphasis that we have is really a focus on precision over recall. It's in some ways harder to get high precision models, so we're really focusing on that for the competition. And as you see in the notes down here, Lark has been able to get more than 78% precision, and really that was just for a fairly straightforward TF-IDF approach. Even though there could be much more substantial forms of machine learning modeling, they took a very simple approach and were able to get almost 80% precision. KAIST, on the other hand, has been applying some of their current research. They're using document QA to have essentially use deep learning for question and answer. So they can train on data sets and publications and then pose questions to the QA system. And this is using some of the more recent work on transformers. Obviously, since 2018, there's been so much work since early 2018 on the Sesame Street of transformers, Bert, Ernie, etc. Elmo starting that out. So it's very exciting that a lot is happening, and this area of natural language is a lot where my background is. Just even recently, there have been large advances. I'm sure probably many of you have read the papers about how these models have become so large and so complex. It's actually becoming difficult to reproduce results from Google and Baidu and others. And also there's the matter of carbon footprint. If you've seen the paper about energy and policy with regard to deep learning models in natural language, currently, if you're training GPT-2 with neural architecture search, the amount of cloud computing required to train a model from scratch, the carbon footprint on that is approximately 5 times the carbon footprint of running an automobile for its entire lifetime, including all the fuel used. So there's a lot of concerns about where natural language is headed, but yet you also see things such as the Merity's recent paper on the shared attention head. We're getting essentially some diminishing returns by having enormous complexity in models, almost billion parameter models when you look at Megatron. But yet you also see shared attention where we're pulling back and we're able to do very substantial work even on single server. So this is, this area of natural language, it's very closely associated with, say, entity linking. And I'm very excited because, again, with the whole Sesame Street thing of Bert, Ernie, Elmo, Alberta, etc., there's just been so much progress. And now we're starting to see other research efforts that are leading to a lot of progress on efficiency. Now, there's another aspect, as I mentioned before, repeatedly, we look toward ways to include expertise, human expertise, providing feedback loops. And so one of these is where we take the models from the competition and we can infer missing metadata, what are the links between data sets and research publications. The goal there being that we could take millions of PDFs, run them through the models, and then be able to infer the missing data set linkage. But then we can use semi-supervised learning to identify, where do we see uncertainty in those results, and take those and feed those back to the actual authors. So for instance, REPIC is scholarly infrastructure for economists. If you're an economist, most likely you have an account on REPIC. Definitely your papers are represented there. And so we've been partnering with Repic, with Christian Zimmerman, who produces Repic, to take our inferred metadata, run it through authors on Repic, and get their feedback. Is it correct? Is there something missing? And this is great because now we've got a way to interact with authors, to confirm metadata, and it provides ways of expanding other types of feedback loops. There's an article down below about using semi-supervised learning, one that I did as an overview, but also the original blog post from Christian Zimmerman. And we are looking at expanding this out. We've been talking with ResearchGate and with others about the possibility of working with other author communities beyond economics, working out, branching out into other domains. And then in summary, have a few links here for additional information. On the right-hand side, there are several different articles and presentations that we've had recently that describe rich context and adjacent work at Bundesbank and others. One of our colleagues, Ian Mulvaney, has been lecturing about this at Force 11 and others. Some really excellent presentations from Ian. In terms of rich context, our website is coleridgeinitiative.org/rich-context. We have a white paper describing this, and there is a book coming out. It says January 2020. We were just talking to the publisher about the cover today, so we're hopeful this will be coming out really within the next couple of weeks. And also, there's a link there as far as getting involved with the project in many different areas. And I think that this is our last slide. So from that point, I'll cut over. We'd love to discuss with you more. Are there any questions?
Okay. So thank you, Paco. And we would invite questions now. So anyone, if you have any questions about this ML leaderboard competition, you can ask now if you want. So, hi Paco, I have a few questions. Yeah. So, when you were releasing the data, I was curious about how are you going for parsing the PDFs? Because you said, yeah. So that's a big challenge for information extraction from the research articles, right?
Very, very definitely. Let me dig up. I have some notes there. Let me dig up here. So that's interesting. In the book, several of the teams, all of the leading teams, contributed chapters to the upcoming book, and they described their methodology for being able to do their feature engineering, their preparation of the data, starting from a corpus of PDFs. And let me dig up one of the latest here graph. Okay, great. So what was interesting was we found that multiple teams had really converged on a similar type of approach. We had Allen AI and then also Lark out of Singapore Management University. And they had all used a tool from, let me take this up here. They had used a tool coming out of Allen AI that was called SPV. And in particular, they had both used SPV version 2. It's interesting because SPV is fairly sophisticated in terms of doing text extraction from PDF. I can imagine a lot of people here have worked with that. I've definitely struggled on different projects with parsing PDFs. It's non-trivial because of the event-based nature of how PDFs are constructed. And also what we found is that you don't just need the flat text, you really need to have more of a semi-structured approach. And so, one of the problems we struggle with there is when you're parsing a paper, can you get it broken down into, here is text that came from the title, here is text from the abstract, here is text from the method section, here's text from the conclusion, text from the bibliography, citations, etc. And so SPV, there was SPV1, which was a way of doing that kind of semi-structured parsing. SPV2, if I recall right, I believe it uses by LSTM, and it has much better predictive quality as far as working with the text, although SPV2 is no longer supported. And so in terms of our current pipeline, frankly, what we're looking at now is replacing that. There's something called GrowBid, and that I'll dig up where that comes from. And then there's another one called Parser that comes from the AXA group. And GrowBid is it's based on JVM. I'll dig up to read the docs for it here. Yeah, let me dig up this other one here. Yeah, great. And let me dig up this one. So I can share my screen real quick and show. I probably have been sharing my screen the whole time. There we go. GrowBid is a service that you can run. It's JVM based, and so essentially you're setting up a server. You can run it in a Docker container, and then you can run either as a service or a batch mode to be able to do parsing. I've been looking into this and looking at a number of different like PDF. There are several different versions of Python-based or JVM-based parsers. Frankly, the people who really lead on this were, if you're familiar with Chris Ray's lab out of Stanford, the one that did Deep Dive, they're probably the most advanced in this particular area. And Deep Dive project led to something called Snorkel, which is weak supervision, a really excellent open source project for AI. But it also led to a commercial company called Lattice that Apple acquired. And I talked with Chris Ray about how they were approaching this. And frankly, they said that they had just licensed Adobe Acrobat. But that's very expensive. Stanford could afford it. So I've been looking at better means of being able to do that kind of parsing. And the best thing that I've seen so far is this is out fairly recently. It's called Parser. It's from AXA. And it will parse into JSON or Markdown. It's Python based, a lot less dependencies, and I think that this is probably going to be the way that we work into our workflow for that.
Okay, thank you, Paco. And I have another question. So. How you could think of integrating your efforts towards the efforts that are done with Google Dataset Search or Zenodo for hosting the datasets or Figshare. So do you think a kind of overlap between your efforts and theirs?
My apologies. I had some garble on the audio on Skype. Could you repeat the last part?
Yeah, so I want to know that how could you see an overlap of your efforts with the public dataset hosting repositories like the Google Dataset Search or the Zenodo or the Figshare? Yeah, so can you comment on that?
Excellent. Yeah, that's great. Well, I believe that we're seeing an evolution of thinking about data sets. Certainly within the Jupyter community, but elsewhere in research, there's a lot of drive toward having more reproducible research. This is important in academia as well as important in industry. So for a long time, I led data teams in industry, and one of the issues there is that if you can't reproduce results, you get into problems where a team in one part of the company will see drastically different results than a team in a different part of the company, and then the leaders see some sort of disparate recommendations. So reproducibility has become a key issue in research as well as in industry. And I believe that part of where the world is heading right now, part of where the landscape is changing, are to see, really incrementally at first, but then probably much more substantially later, different pushes toward reproducibility. And in particular, when we look at excellent services like Google Dataset Search or other means of having some type of metadata about data sets represented publicly, Datasite has their efforts toward that, and we're working with them as well. I believe that a lot of the drive for that is the matter of reproducibility. So understanding that for a given research project, we have the dataset dependencies. We may have configuration dependencies. So can we capture, for instance, Jupyter notebooks, but also the configurations of the kernels that were used for them? I don't know if you've seen, but there's a new project out of GNU, which is called GUIX. Yeah. Yes.
From a practical point of view, the reason for reproducibility is that it reduces the cost of search and discovery. So it reduces the cost for scientific agencies. We have been working pretty closely with National Science Foundation to the extent that researchers and analysts can find data sets that have been used before and find the code. It improves the efficiency of science and the quality of science. On the evidence-based policy side, even for something as straightforward as Lyft, which is a ride-sharing platform, where there are only 1,500 data sets and a limited number of data analysts, Mark Grover estimates that 35% of analysts' time is spent on searching and discovering data sets, to the extent that search and discovery cost and collaboration is reduced, and I would guess in the government case it's maybe 50% of time. Again, to put it in context, the United States GDP is maybe 20% of economic activity in the world. Federal government, federal, state, and local government is about a third of that activity. To the extent that you're able to reduce those costs, you can have a major impact on wasted activity and reallocate those substantial resources to more productive use. So I'm just translating the technical aspect into the practical aspect. So that can work in India, in any country in the world. So this is really your chance to have a massive impact at an international scale. We're working with the UK, with Germany, obviously in the United States. And Paco has the tools and technologies that can play a role here. Sorry, Paco, I just wanted to motivate it. Yep.
Oh, fantastic. Thank you. And also that ties back into what we mentioned about Jupyter, the strategy for these extensions, and also about the end goal of recommendations. So if you're familiar with some of the current research in machine learning in terms of AutoML, one of the areas of active research is something called meta-learning. And one of the ideas there is that if we can collect a database within an organization of how analysis has been run, we can learn from that database so that when analysts go to do new work, we can apply AutoML techniques effectively to recommend configurations of analytics workflows. So to bring this all together then, as we see analysts working in platforms such as ADRF, and we collect history of how they're doing the analytics work through Jupyter telemetry, we collect that into log files, we build a database for meta-learning. Then, when new analysts come in to do similar work, we can recommend to them what are the data sets, who are the people they can talk with to learn from, but also what are the initial configurations they should start with so they don't have to start from scratch every time and reproduce those learnings. As Julia, cost for data science is just relearning about the data sets over and over.
Okay, thank you, Paco. And any questions or comments? I have one last question. So, I guess you are familiar with the with Carl Malamud's work on the JNU depot, where they have been storing a huge amount of research articles which are somewhat behind paywalls and the articles which are unpaywalled. So I think they are offering services to mine that huge amount of data, and that would be a welcome step for someone to pick on those steps. Yeah. So that's just a comment on what something is going on in India. It's called the Jawaharlal Nehru University, where Karl Nathan has been building a database of huge. There was a recent Nature article on like processing text mining research articles which are behind paywalls, and yeah.
So you're talking about Carl Malmud?
Yes.
Yeah. Carl and I used to be we're neighbors. We used to be office mates. I live in Northern California, so well, Carl effectively lived here, but yeah, we used to share an office space up until about 2 years ago. I know him very well. He's a good friend, and I am thrilled with his project, and I believe that yes, what we're building would fit in there very well. And similarly, we're looking. Oh, sorry.
We actually reached out to him for the workshop. He was on travel. But I also worked with him when I was working on the open data strategy when that was in the Obama White House. He was quite involved with that conversation.
He's wonderful.
Right. Okay, so if you don't have any more questions, so we can thank the speakers for their valuable time. So we thank you, Paco and Professor Lane, for having time with us, and I hope Paco will be talking to us again in February. So thank you so much.
Well, thank you all for staying so late. It's late there. It's 7:45, I think. No,
Yes. Right.
7:45. Is it?
Yeah, it's 7:15 in the night, but it's still okay for us. Yeah.
Thank you so much, and thanks for staying and being interested. If you have any questions, please email us, get in touch with us. My email address is julia.lane@nyu.edu. Put in the subject line that you attended this presentation, and Paco, give them your email address.
Yes, certainly. My email is paco@darwin.ai, and I'll forward that as well along with the slides. And I really look forward to talking with you next month. I'll present about PyText rank and graph algorithms for entity extraction.
Thank you.
And you can also reach us in LinkedIn, which is how I met Tirthankar. So, thank you, guys.
Okay, thank you.
Thank you very much for the opportunity.
Thank you. Bye-bye.